Here we go, let's do another problem. We have a function that is an absolute value function, and when we consider using the extreme value theorem, we have to think of where the derivative equals 0, where the derivative doesn't exist, and the endpoints of an interval. So let's just go ahead and go for the obvious. We're going to consider those 2 points, right? So in a minute, we're going to have a little chart, and it's going to say this, and there we go. Oh, one thing I didn't talk about, if possible, is this function continuous? Yeah, it's continuous. We don't have any discontinuities, nowhere where we've divided by 0. We've met all the conditions of continuity everywhere on this function. So I would love to say the derivative equals blah, 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 but let's just use our knowledge of what this graph looks like to deal with it. So I know what this graph looks like, and so do you. Absolute value graphs are shaped like this. And this one is actually kind of steep. Not that the steepness is going to impact the actual computations here, but the 2 takes it from a slope of 1 and -1 on each side to a 2 and -2 on each side. And this x plus 4 is going to shift the function to the left 4, and so we have this deal going on. And it's going to go all the way back here to -10 and all the way up here to +10. Figure is not drawn to scale. Okay, and it's going to just keep going. So just looking at that and knowing we have straight lines on either side, because its absolute value is a piecewise function with 2 linear components. That's piecewise linear, just saying. I think we've been through that. Anyway, looking at that, we don't have anywhere, let me rephrase this. I was going to say that differently. Let's actually word it this way. Well, we don't have anywhere that the derivative equals 0. This derivative will never equal 0. You never have a slope of 0, but you do clearly have a place where the derivative doesn't exist, and it's at the vertex. It's at this point right here, and that point is -4. It's where this stuff, this expression in the absolute value would equal 0, so it would be -4. That's it. And that's all I have to consider, because again, we don't have any curve here. There's nowhere where the derivative would equal 0. These are 2 straight lines. So let's plug this in. This would be a great calculator inactive question, so let's do this in our head. I'm going to go for the obvious. Plug in a -4, you get 0. So to me, I already actually know the minimum. You can look at the graph and tell that that's the minimum. So the absolute minimum is -4, 0. Okay, let's figure out what happens if I plug in a -10. -10 goes here. That gives me -6 becomes +6 times 2 is 12. And 10 goes here is 14 times 2 is 28. And that is pretty straightforward. I think we have found the lowest, clearly. We also found the highest. And again, they asked for the absolute maximum and minimum values of each function. So you could get this problem wrong if you say, oh, we found the minimum value, it's -4. No, that is the x value for the location of the minimum. The minimum value of the function is 0, which we have really addressed all that in this little phrase right here. Okay, enough of that. Absolute maximum is 1028. There we go. All right, let's do the next one, which is, ooh, evil. This one's fun. 2x e to the x from -2 to 1. This one's going to get gross, y'all. 2x e to the x from -2 to 1. Okay, now clearly I'm not going to graph this one and be like, yeah, we all know what this graph looks like. No, clearly we don't. We can graph absolute value, and there are very few hands that go up in the room. Graph that one by hand without a calculator. Ha, you're right. It's not as painful as you might think, but it's not as obvious. What we are going to do, though, is figure out, first of all, if the extreme value theorem is applicable. The extreme value theorem, again, is one of our 3 existence theorems. I think it's good to kind of pause and say this here. We have 3 existence theorems. You've heard them a lot, and here they are. The intermediate value theorem is a fantastic way to prove that I have a y value in between 2 other y values. I have to meet 2 criteria. I have to have betweenness and continuity. The mean value theorem is a way that I can prove that the slope on an interval equals the average rate of change on that interval, but I also have to have continuity on the interval, continuity on the closed interval, differentiability on the open interval. And making sure I said that right. It's true, yeah, I do. And Is it? Yeah. And then for the extreme value theorem, my mind went blank. For the extreme value theorem, we need continuity, simple continuity. This function is continuous. So we're good. We're good. Right. So again, let's move on. I'm going to take the derivative of this, and so are you, and it's going to be fun for both of us. Yay, what fun this is. The derivative f prime g plus f g prime. And I would love to set that equal to 0, and I will, but let's just keep going with the fact that I know there's a greatest common factor here, and it's 2e to the x, and that gives me 1 plus x, and that will equal 0. So basically, I went ahead and factored, because it's factorable, there's a greatest common factor of 2e to the x. Factored it out. So if this equals 0, then either 2e to the x equals 0, or 1 plus x equals 0, and we have to consider all our options. Let's go for the obvious first. Let's go for the not so obvious second. E to the x would equal 0, divided by 2. And e to some power gives me 0. All right, let's just stop, think about it, use our previous knowledge here. E to the x, the graph of e to the x is exponential. An exponential graph does this, the exponential growth in this case. It will never touch the x-axis. Never. Never, 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 never going to touch the x-axis. So it's not going to happen. This is not going to work. If you did not realize that, and that's fine, you can rewrite this as a natural log. Grab a calculator if that's your thing. You'll type that in, you'll get an error message. So just don't, okay? Not going to work. Technically, this is an untrue statement, this is an untrue statement, and you will have no solutions from this. You do have a solution from this one. So again, we are considering everywhere the derivative equals 0. That comes from this, nothing here, nothing special here. Also the endpoints of the interval, and everywhere the derivative doesn't exist, but this derivative just exists, okay? It exists at any given point. There are no x values that are forbidden, like that would create discontinuities. So let's make a little chart. I'll stand in your way so you can't see it. That's what I like to do. You know, frustrating. Leaving plenty of room to work this out. All right, and we're going to plug these values in, and I'm going to go as calculatorless as possible. So let's plug in -2. So I'm going to have 2 times -2, e to the -2. And I'm going to rewrite that. I'm going to write that as -4 over e squared. Now, at this point, you're probably tempted to grab a calculator. I'm not. Hang with me here for a minute. Once we're done with this, we'll actually pretty much be able to tell which one of these is the biggest, which is the smallest. We're going to plug a -1 in. That gives us -2 e to the -1, which is -2 over e to the 1. And then we'll plug in a 1, which is 2 times 1 times e. So 2e. Okay, I think if I looked at you right now through the screen and I said, hey, I'm making eye contact with you. Hey, find the maximum. You could find it. I have no idea what the decimals are for the first two, and the third one I have just a very rough guess, but you can still find it. That's the only positive. It's the only positive. So I know my maximum. There we go. So my absolute max is at 1, 2e. My absolute minimum is, okay. All right. Let's consider magnitudes of denominators. Now we can look at numerators as well, and we'll say, well, -4 and the -2. Okay, which is bigger though? Which is more massive? E squared or e? Okay, e squared is bigger. We have a larger denominator here than we do here. So because of that, I think this one is actually not as small as this one, okay? The larger the denominator, all right, got to word it carefully. I'm ignoring the negatives for just a second. If these were positive, then this one would be, I might have misspoken a second ago, so hang with me on this. If I'm ignoring the negatives, the larger denominator is this one, by far. So whatever the difference in numerators is, this denominator is large enough to compensate for that. I'm going calculatorless, and I'm just walking you through what happens in my head. And so I look at that and say, well, 4 over e is going to be smaller than 2 over e. You can also think about it this way. 2 over e, well, e is 2.7, right? So you have 2 over 2.7. That's almost 1. E squared is, if I'm not mistaken, 7 point something. So we have 4 over 7. This one is larger, ignoring the negatives. Making them negative, this one would be more negative. All right, calculator time. Sometimes you can logically think through things. Negative 4 over e squared is, oh, that's what it is. Aren't you curious? I'm not telling. Negative 2 over e to the first, there we go. So in case you care, and I'm going to use my 3 decimal places here, negative 0.736. Negative 0.736. This is negative 0.541. And so therefore this one is the lowest, and the minimum is negative 1 comma negative 2 over e, or the decimal equivalent. There we go.